Okay, hi everyone. So for those of you who were not familiar with where Heidelberg is located, I always like to include a little map here. Oh, here it is. You can kind of see it here on the screen, so you can see where, like I said, about an hour and a half to 2 hours north of here, almost directly, but not quite. And what I want to do, you can see this is a much longer title than what was in the agenda, because I'm going to talk a little bit about our trends and our watershed data, and then some of the research on our phosphorus stratification. So I've expanded a little bit, hopefully for good reason. And the reason I'm doing that is because we're mostly well known for our tributary loading program. We've been monitoring rivers all around Ohio and up into Michigan for lots of years. You can see right now this is the map that shows all of our current locations where we're collecting water samples. If you counted all the dots, it's around 23, depending on how you decide to count some of the stations. At each one of these locations where we're collecting water samples, we're working with USGS to get the water quantity, so we only have to worry about the quality side of things. And our very longest term data is from, well, I swear this thing was working a minute ago. From the Maumee River here, the Sandusky River, we've been monitoring those locations since 1974. We added other stations like the Raisin and the Cuyahoga and some sub-watersheds in the early 80s. These three that are in the bottom go down to the Ohio River, and so ultimately Gulf of Mexico, so they're not so much Lake Erie, although that's pretty much all I'm going to focus on. We added those in the mid-90s, and everything else was since then. Say what?
Just want to make sure you don't turn off the microphone. The switch is down there still.
Is it supposed to be up or down?
I think it's up. It's on. It should say now.
It doesn't say, but it's up.
Oh, really? Well, up's good then. Just,
okay.
Yeah.
And so the way this works is, if you went to any one of these red dots, we have a building by a river. There's a pump in that river that pumps water essentially in a flow-through system, and that flow-through system is sampled with a refrigerated ISCO autosampler. We collect the samples pretty much every Monday, and then we analyze them for all kinds of things. I'm only going to really talk about phosphorus and maybe nitrate, but we monitor also other anions, some pesticides, and suspended sediments. And so I'm talking about this for Lake Erie specifically. I don't probably need to hammer this point home too much, but it's because of this return of blooms. Lake Erie had blooms. They went away in the mid-90s, and they since returned pretty intensively. So this is showing some of the satellite images of the 2011 bloom. And what we know so far with these blooms is that they're very closely correlated with the loading of phosphorus from the Maumee River. It's the largest watershed that goes into the western Lake Erie Basin, but mostly only from March through July, right? And I have here total bioavailable phosphorus load, which is essentially all of our dissolved phosphorus, or DRP, and about 8% of the particulate phosphorus, right? So it's the phosphorus that's available from particulates that we've done some extractions on, as well as the positional bioavailability, so what we think is actually making it into the river. And so you see this is a pretty good relationship, and we use this to then forecast the blooms every summer. Our bloom forecast happened in earlier July. So why did the blooms return? What have we been seeing over time? And so I first wanted to start, this is all Maumee River, because that's the driver here. First wanted to start with flow, right? This is just discharge from the spring, March through July, and I have them in 5-year increments. So it's a 5-year average with the 95% confidence intervals. And what you see is that there's some variation, of course, a lot of variation, but there's a general upward trend over the past decade when the blooms returned. But most of our change over time, over the long time frame, has been in flow weight and mean concentrations. So it's that spring flow weight and mean concentration, and you can see it was very high, jumped down in the 90s when we didn't really have any blooms, and since increased, and it's remained high. So what's interesting is that over the past decade or so, we've been sort of stagnant on our flow weight and means, but high. So if we put both of these together, our loadings over that period of time have largely been increased over that time period. I was supposed to mention, and I forgot, the dotted lines are the annex for target concentrations and loads for Lake Erie, so we don't want to exceed that. The flow weight and mean is kind of where we want to be. The loading is when we don't want to exceed. If we don't want to have a bloom that's worse than 2012, which is basically no bloom at all. Okay, so we see these increases, but most of the change in flow weight, this point being that, so we see these increases in the recent decades, but when we do some better calculations on this, really only about 35% of the increased load is associated with this increase in hydrology or increase in discharge. The rest of it is really associated with this big increase in flow weight and mean concentrations, which kind of started off this increasing trend in loadings. Okay, so those of you who've seen me give this talk, I just reconfigured the data in a slightly different way, so hopefully it'll make it a little bit more exciting to see me say the same things over again. Okay, and so let's do the same thing for total phosphorus. You can see flow weight and means on total phosphorus are quite different. They were high and they've mostly been trending down. Of course, over the past couple of decades, it's been fairly stagnant. What's interesting here is for flow weight and mean concentrations, we've never been down at the target level. Right, this is something we've never achieved. So we can then ask how these targets were developed, but that's not the point of this workshop. And then if we look at the loading, we do see that increase due to mostly because of increases in flow and increases in erosive capacity. Okay. And then for this year, how did this year compare to the rest? You know, we've done all of these things in the land, and everyone keeps asking me this question, well, how are we making progress yet? So I've decided the easiest way to do this is to correlate loading versus discharge. And this was in part inspired by Rem, because he was doing this for Old Woman Creek already. And it was also because I've had this challenge. Flow weight and mean is somewhat related to how much flow we get in a year. So we have years like this year where flow weight and mean is slightly lower than where it has been in our really big years. And so it's hard to tell, well, is it low because of lower flow, or is it low just because we're actually doing something? So you can see here, 2018 there in yellow is exactly on the line. Now, I have some pop-ups here. Basically exactly where it's on the line, so it's exactly where you would expect the loading to be based off of what flow we got this year. So we got a moderate level of flow. I'm going to try this again. Nope, still not working. We got a moderate level of flow, not nearly as high as what we've seen in past years. I did include these just because we know these are autocorrelated, right? And we know then that this slope, being nonlinear, is an indicator of what the concentration is. And we can see the same thing. And so what you see here is, again, that loading target. That's a static target. If we exceed it, there's a bloom. If we're below it, there's not a bloom. So what you see is that there's certain scenarios where we get so low flow that we're going to meet that loading target, which is why we set a flow weight and mean target for the lake. As you can see, that's a moving target here. And this year, neither met the loading target nor the flow weight and mean target. We can do the same thing for total phosphorus and see the same scenario where we got exactly the amount of loading for total phosphorus we would have expected based off of the flow we got, meaning there's been no change in concentration, and that we are nowhere near any of the targets that we want to have set. So that's the bearer of bad news, right? And because of that, because we had a moderate flow, we're expecting a moderate sized bloom. It's a bloom of 6 on a level of 0 to 10 or 10.5. So it's not going to be the very worst. It's not going to be low either. And the variation there is depending on how the models decided to deal with the data we gave them. So let's look at what the raw data looks like for this past spring. So this is showing from February through the end of July, Maumee Spring hydrograph. The first thing I want to show you, you see, most of our flow happened in February. This was rain, not snow melt, so we did not get very much snow this year. And then we had some later season rains, nothing in July. And what we see, this is dissolved phosphorus concentrations, DRP, same thing as SRP, just whatever you like to say. And what I really want to point out here is it's very clearly non-point sources, right? You see an increase, comes down to nothing, only increases when there's flow. But what I think is interesting here, and a point that I think Kevin and I have both made multiple times, is that we don't really see a huge change in response of DRP depending on storms over this season, right? This big storm here It goes up to about, 0.1 to 0.2. Same thing here, right? We did have a little bit higher in that middle period when there was some planting, but, really this is not a whole lot of change in responsive DRP based off of flow. So we're seeing very consistent increases here. The difference being something like nitrate, where you see that early on we get oftentimes dilution, some increases, and then we get a big flushing event in June associated with side dress nitrogen applications. So I also want to show you that this happens over time. Now I'm going to a smaller creek. This is Honey Creek instead of the Maumee River because it points out some interesting things. So we're going from 2012, 13, 14, and 15 in water years. Still DRP concentrations. You can still see the flow in the background here. The two things I want to point out is some incidental losses. This is high concentrations we got because fertilizer applied and then it rained and then it washed off, right? But if you take those away and you look at all of these years of data, pretty much everything you see is that we go up to about 0.2 milligrams per liter, no matter what, right? Doesn't matter if it is in the middle of winter, in the middle of the summer, if we're getting down into the fall, if we have a wet summer instead of a very dry summer, doesn't matter. Always goes up to about 0.2. And so what this suggests is that there's a large source of phosphorus available to run off if there's water going across the ground. So the question is, well, is that high soil test phosphorus? There's not a whole lot of data to support that. The data we have on soil test phosphorus suggests that it's about around where we would recommend phosphorus to be, depending on our existing soil phosphorus recommendations. So that's led us to looking into the soil phosphorus stratification issue. So why would we think that this could be an issue at all? And mostly it's because the main thing, one of the big things that's changed from the 80s through the 90s into today is a switch from this very intensive moldboard and virgin tillage to a high residue rotational no-till, right? So I have one side versus the other. Clearly, if I was able to take this picture, there's still people doing moldboard plowing, but not very, very often anymore. We do broadcast phosphorus in the fall. That has always happened. It's just, it used to get very well mixed and it doesn't so much anymore. And so the idea of this is, well, we know that higher soil tests lead to higher dissolved phosphorus in runoff, and that there's been plenty of studies that have shown us that switching to a continuous no-till leads to these big losses of dissolved phosphorus. But our question is, this is not continuous no-till. This is rotational no-till with conservation tillage, right? There's disking and chiseling. There's no inversion, but there's still ground working. Is it possible? Can we actually see stratification develop in these soils under these scenarios? So what we did, I say we like I was there. It was before I even started at Heidelberg, about 10 years ago. We went and sampled over 1,500 farms throughout the Sandusky River watershed. Something like 85% rotational no-till, very little of anything else. And we used CCAs to help us do this because Lord knows we could not, with our small group of people, sample quite that many farms. So what did we find? Well, this is just showing box plots based off of soil depth, right? So we have 0 to 1 inch, 1 to 2, 2 to 5, and 5 to 8. This is our 4-part increment test. Most of the time we just did 2 parts, so that's why the N is only 200 and not 1,500 or, well, 1,739. But what you see is very strong stratification. You see the medians here. What was interesting is that across all of our tests, the median soil test value, if you use the 0 to 8 inch core, so what we typically recommend in our region, was the 35 ppm. So right in the middle of agronomic ranges, but our median 1 inch was 60 ppm, which is almost twice as high. Right? The stratification was significant, but there were some cases where we didn't see a whole lot, right? There's some cases where, especially under high soil tests, it was basically the same thing all the way through. So what we did was we also looked at these two relative to each other. What did the top 0 to 2 inches look like relative to the 0 to 8 inches? So could we predict stratification? 4 minutes? I'm almost done, it's fine. Could we predict stratification if we knew the soil test level? So you see the 1-to-1 line. So most of the time you can see we're above that 1-to-1 line, indicating there was stratification, and went all the way up to being 3 times higher if you looked at that 0 to 2 inch. But what I would say is you could probably throw a line through that and say it's well correlated. You would, violate equal variance assumptions, but I still would say you really can't, because let's pick a soil test, right? Let's say we pick 50. All right, so you go and you say, oh, in any field that has 50 ppm, based off the data we collected, that top 0 to 2 inches could be anywhere from not at all stratified, like 20 ppm, to 140. So how do you predict that based off of your 0 to 8 inch? So our main case from this paper, it's already been published, it's in JAQ, is that we really should be looking at both of these, both the 0 to 8 inch, because that's what soil test recommendations are based on, but also a 0 to 1 or 0 to 2 inch, because that is going to be environmentally relevant. So the big thing that well, I would say Dave's baby in this paper, if you guys know Dave Baker, he's a big thinker. And his thing was to try and scale this up and see how much stratification could possibly matter. So essentially what he did was he took the cumulative distribution of that 0 to 2 inch and the 0 to 8 inch. Actually, I think it might have been 0 to 1, but that's fine. And compared the two, and then played with different scenarios within that cumulative distribution to see what would happen. So essentially what this ends up doing is it assumes things that I'm sure a lot of you probably would not agree with, and I'm not sure I would either, but one of them is a linear relationship between soil test phosphorus and DRP runoff. And in doing that, it assumes that, for each unit of soil test phosphorus, that's a unit of DRP runoff risk, if you assume that those two are correlated in that way. And so the first thing that you can say is that, well, if you're looking at the 0 to 2 inch and not the 0 to 8 inch, the risk of DRP runoff looks 55% higher. It's a fancy way of saying, well, if you look at the 0 to 2 inch, it's a higher median soil test level, so it suggests that there's a higher risk for runoff. But then you could do things like, well, what if we took all of the fields that were over 40 ppm and reduced them to 40 ppm? How would that change this percentage of risk of runoff? Well, what he came up with is that it would be a 15.3% reduction in this runoff risk, but it targets 40% of the fields. So basically, we said in our data set, 40% of all of our fields were over 40 ppm. And so that's a lot of fields. One thing that it points out to me is that targeting the top 20% of fields is probably not going to get us to where we need to be, right, in terms of some of these target reductions. But the other thing is that we could target stratification instead. So what if we took that 0 to 2 inches, anything that was 20 ppm higher than if you looked at the 0 to 8, and we made it 0. So there's no stratification. It's perfectly well mixed. And in his eyes, this would be an inversion tillage, right? Which is not something that I see happening in our region anytime soon, but it's a thought. It's a thought process here, right? And this would lead to a 28.5% reduction in DRP risk. Targets more fields, of course, because most of them had some level of stratification. But the difference being that this would be drawdown and would take some time, and this could be done immediately, right? You just do it and it's done. Unless we do drawdown. But we know this ignores big things. The big one is preferential flow. The second one is those incidental losses. I don't think that's a huge deal based off of our watershed data, but the preferential flow I think is a big one. So let's put it all together into one big summary. What I think is missing from this analysis is the macropore flow, and I think I'm hopefully leading right into Kevin's talk perfectly well. I think that is huge. That's the only thing that makes stratification matter. If we didn't have preferential flow, stratification wouldn't matter at all, I don't think. So where I would say if we had a field that I would think would be high in terms of DRP loss, it would have soil stratification, macropore loss, tile drains, in our Western Lake Erie Basin watersheds, which I think is an awful lot of them, but I think what's controlling all of it is that connection with the tile drains. I put a big rain cloud up there because the other thing we know is that the intensity of storm events have increased, so it makes these connections even more strong, I would say. So with that, hopefully it's enough food for thought. This is all of my contact info, and we'll discuss later, I think.
How are we good on time?
Yeah, we're good at that.
Yeah.
Time for questions?
Yes, we do.
Okay, so we might have time for questions.
Sweet.
Yeah.
And if you have your questions.
Were there any questions? I feel like I'm talking into a mic, but I'm not talking into a mic. But I am talking into a mic.
So if not, we can also.
What you got, Chad?
I'm really interested in the contribution of incidental losses. I thought this had a lot of I would love, I don't know if it's possible to know.
Yeah.
Do we have any idea, being able to quantify the source of incidental losses versus soil dissolved loss and legacy loss? To say that one
Yeah.
source is more important or larger than the other in the long.
Yeah, so just to repeat the question for the cameras, that the question is, can we better quantify these incidental losses versus that sort of chronic or edaphic soil loss for phosphorus, right? Well, it's hard, right? So what I showed you, when I showed you, it's going to take 9 years to get there.
We don't have that much time.
This one, right? You would think I could use this by now. Okay. And really, of all of these years, I go all the way up to current times. The only times we see incidental losses, this is the biggest one up here in 2012, and this is a small creek. Like, this is, even this big event, this goes up to about 1 milligram per liter, which is huge for our watersheds. That's like a point source for the whole creek, right? This sort of scenario, it doesn't happen all that often. We saw it here in 2014. I really haven't seen it since. So the question is this sort of an event happening very often? And I would say no. So what I think is tricky is when you look at like Kevin's edge of field data, the variation in people when they apply their fertilizer and then the rain-off events relative to when they apply it, I don't think that it's consistent enough across all of the fields that are applying in a watershed for us to see it very well. So I think the only real way to be able to do it would be using some other type of tracer. We've played around with folks from Bowling Green doing stable isotope work, thinking, well, maybe that would be the way to be able to separate that out a little bit. And it is proving to be far trickier than you would think, just because, oxygen isotopes interact with all kinds of things. And getting those sources separated to be able to do any sort of percentage is tough. So I don't know that I have a good answer for you on that.